All right. Hello, everyone. Welcome back to Operating Systems. I hope that you are all doing okay today. I hope you're all doing okay. It's warmed up a little bit outside. It's supposed to snow a bunch today. Maybe that's changed. I'm not sure. It is Winnipeg. We're living in Winnipeg. Yeah, okay. So let's talk about operating systems today. By the end of today's lecture, what I would like you to be able to do is apply concepts like design by contract, automated testing, memory management, and debugging. I want to finish up a little bit more of this linked list thing that we started working on last class. And I want to finish up specifically the idea of using something like lldb to help remind you about debugging on the command line when you're working on Aviary. If you can figure out how to get VS Code to do C debugging remotely, awesome, please tell us. But I know how to use lldb, so that's what I'm going to use to kind of demonstrate this idea. I also want to do at least one test. I want to at least write one test. Again, this entire exercise is very much, let's dust off cobwebs from Comp 2160. If it's been a while since you've done Comp 2160, it's a lot less about building a linked list. I'm super confident that all of you can build a linked list in C at this point. The other thing that I want to do is I want you to be able to, at least at some beginning level, I want you to be able to describe how an operating system manages processes. This is a keyword that I've used a couple of times. I've used this a couple of times. We're going to talk a little bit about this today in the context of the material that we're looking at next week, file systems. The very introductory part of that kind of tells us a little bit about processes. And in order to drive the file system stuff, I want us to have some minimal idea of what processes look like on a system and what kinds of things the OS is doing to manage processes. We're going to spend a lot of time looking at processes later in the course. We're going to spend a lot of time looking at memory later in the course, but I want us to have some basic idea of what this looks like as we're getting into file systems, just so we have this idea in our head. So let's get straight into this. I want to pick up where we left off last time with working on this linked list structure in C. And so I'm going to continue working where I left off here. So what we got to last time was we had built up this invariant for the list structure. We didn't make an invariant for the node structure because we don't really have much in the node other than a single integer. There's not really much we can validate. Next is either null or it's not. And those are values that we really can't say like confidently that's what makes a valid node in this case. The other thing that we did here was we implemented a constructor-like function. And the things that I want to point at in terms of what we're doing here for defensive programming and for things like design by contract is defensive programming here is I've done memory allocation, dynamic memory allocation with malloc here to create a new instance, or at least to allocate some memory to put a new instance of this structure in. Malloc can return null, so I'm checking to see if malloc has returned null before I start working with the pointer that was returned by it. So I'm doing some defensive programming against some other system that I'm working with here. The other system I'm working with is the memory allocator, doing malloc with malloc. The post condition for my constructor function, my create list function here, is that I, the creator of this create list function, I promise to give back to you a valid list. You can assume that what I'm giving back to you is a valid list because I'm making that promise. That's the contract that I'm giving to you. I'm going to shift over here to lecture 3 list, and I'm going to open up my interface here one more time. The other things that I want us to do are to make a destructor function. I want to have an insert front function, and I want to have a size function to query the size of the list that we have. The very first thing I think I want to do is just take a step back for a moment And I want to remind you of one thing that you may not have thought about when you were doing 2160, and that is to use preprocessor directives for doing invariants to make sure that they get compiled out when you are compiling it with that lldb flag. So remember, there's the option when you're doing compilation in C to say -D and then all uppercase lldb, and that says please turn all assertions off. Assertions take time to execute. This is something that's extra that we're doing when we're doing our development, but when we give this to our parents, when we give our linked list to our parents, for them to use for some reason or another, we don't really want to do all that extra stuff. So we want to turn that stuff off, and we can do that with that lldb flag that we passed to Clang. This part where I'm iterating over the list to count up how many nodes that there are in the list and confirming that it's actually the same as the size or the count that I have in my structure, the assertion is the only thing that would get compiled out here. And I don't really want to do this loop every time that has no meaningful purpose. So I'm going to make sure that this also gets compiled out when I do that, that extra flag. So I'm going to say here if ndef ndebug. This is that really awkward like double negative thing here because ndebug says no debug, and if that flag is turned on, or if it is if it's not turned on, I do want to do this, and if it is turned on, I don't want to do this. I'm going to put at the very end here number sign and if. So these are the preprocessor directives that we're using for that. Just confirming quickly at the back, is that big enough for you to see okay? Yeah, okay, awesome. I'm going to go and I'm going to change a little bit of direction here to, I want to start writing some tests for my code. So I'm going to pop open main.c here. Main.c is where I'm going to start writing the tests for the code that I'm writing. How many of you are doing 3350 right now? Almost everyone? Okay, lots and lots of people. One of the things you're going to see in 3350, this is software engineering. One of the things that you're going to see in 3350 is automated testing in the form of like JUnit tests. There are test frameworks like that for C. So don't let me show you this and kind of say there's no test frameworks for C. There are test frameworks for C. I'm not going to use them because I don't really want them to get in the way of our work. There are test frameworks for C. You are more than welcome to use them if you want to in your own assignments, but I'm not going to spend any time talking about them. If you want to use a test framework in C, you're kind of on your own. Testing in C, though, minimally is just like write functions that call other functions and check to see that the output is what you're expecting it to be. This is the kind of test suite that I'm thinking about here. So the very first test that I want to write is one that's going to test whether or not I have, in fact, indeed created a list by calling the create list function. So my test create list function is going to look like this. Test create list. It's not going to take any arguments as input. And the only thing I'm going to do here is I'm going to say int list is equal to create list. I don't pass anything to create list. All I am able to do at this point is see, did I get a non-null pointer back? That's all I'm really able to see based on the interface that I've got. So I can say if list is not equal to null, then I can say that I have indeed successfully created a list. If I was doing this for real, I'd probably do like extra stuff, like I'm going to count how many tests have passed and how many tests have failed. I might do fun things like making pass green and fail red. But for us, for now, just for the sake of this class, this is good enough. This is good enough. I've called my function and I've reported success. Or here, I have reported failure if I didn't actually be able to create a list. All right, and then in my main function, I got to call that function, test create list. I'm going to write this out. I'm going to quit Vim, and then I'm going to make this code. So to do that, I'm going to quickly open up this makefile one last time and kind of remind you of the structure of this thing. You are, again, very welcome to just take this makefile and use it. The structure of this is Make itself knows how to make C programs. It knows how to compile C programs, and it knows how to compile C libraries. When I have a target here like this that's called main, make is going to look in this same directory for a file that's called main.c. It knows how to run Clang because I've told it Clang is my CC, my C compiler. It fills this in as a variable. It fills in all my C flags as part of a variable, and it's just able to run that command for me. It also knows when I put a target like this, list.o, that I'm going to look in this current directory for a file that's called list.c, and I'm going to pass that -c flag to Clang when I compile this and use that as a prerequisite or something that's going to get compiled together with this main thing. So I'm going to quit this, and I'm going to make it, and awesome, we have done it. We have compiled our code. Okay, so using make is just run make, always just run make. This now is, I want to run my test, so I'm going to run my test, and I run main./main. I have successfully created my list. My test has indeed passed. All right, okay. So after that, the other things I want to start doing are the other functions. We have 3 other functions that I want to work with here. So I'm going to pop open my list.h one last time, and I'm just going to start working on this. If you've got this code on your machine, please feel free to follow along with me. If you're happy to just like sit back, put your feet on the table and watch me code, I'm also very happy for that. So the next thing that I want to do here is to implement my destroy list function. This is going to return an int list pointer. But what I've said here is that it's going to return null on success, and it's going to return a pointer back to the list that you passed in if I have failed to do that. So if I was not able to release or free your list for some reason, I'm going to pass back to you what you passed to me in the first place. One of the preconditions for my destroy list function is that the list that you're passing to me, the int list that you passed to me, is a valid list. And so the precondition here is stated in my list of parameters. Must not be null, must be a valid list. So you must not have made changes to the contents of the structure after I gave it back to you in any of the operations that you might have been applying to it. The must not be null is handled by the invariant that I wrote for my list structure. So for my precondition here, I'm just going to call validate list. That's the only thing I'm going to do. I'm still going to behave defensively here. Validate list asserts that list is not equal to null, but if you turn these preconditions and postconditions and invariants off with that ndebug flag, it is conceivable for you to pass a null to me. So I still need to check so that I don't get those magic segmentation fault words printed out to the screen when I try to dereference it. So I'm still here going to say if list is not equal to null. This is a defensive check to prevent against seg faults when these preconditions are turned off at compile time. So I'm going to say if list is not equal to null. Now I need to start iterating the list and deleting all the nodes from the list because I have allocated, or I will have allocated nodes as I go through that. So I'm going to do just a simple list iterator here. So I want to declare a node that's the current node. I'm going to declare that at the very top. And I'm going to set that equal to null to begin with. If my list is in fact not null, then I'm going to say that current is equal to list head. And then I'm going to iterate over the list. I'm going to iterate over the list. So I'm just going to write this out. So I'm going to say current is equal to list head, and then while current does not equal null, I'm going to say current is equal to current. Next, I'm going to at some point have to free current. I will also, I guess, want to make sure that I get a copy of what current is before I do that. So I'm going to say that current is equal to null, and then also I'm going to have a next is equal to null. I'm going to say current next is equal to current next, then I can free it. And then current is equal to next. So the steps here are keep track of what next is, release current back for use by other things, and then make current be the next one. This will let me go through the whole list. I'm going to add something here that says, I want to make sure that every time I remove a node that my list is still a valid list. So my list should always be in a valid state after I've made some modification to it. So I'm going to say validate list here. After I've removed that node from the list, I want to validate my list. I want to make sure that it's still in a valid state. There's an error here, and I'm putting this error here on purpose so that we can use our debugger, but I'll get back to it. I'll get back to it. So after I've done that, then what I want to do is I want to return something to you. And what I'm going to return to you is going to be either null or the list. Those are the two things that I could possibly return to you. So I'm going to say I want to free my list if I've gotten to the point of saying that it's not null already. And then what I'm going to say is list is equal to null after I've done that free. Then I'm going to say return list. So if there was an error, if list is null, I mean, this is kind of a weird state because it's kind of saying if list is null, then just return list. If list is not null, then also return null. It's fine. It doesn't really matter. The purpose of this is so that I can say list is equal to destroy list and then check to see that it's been destroyed. Check to see that it's been destroyed effectively by the thing that I've got. All right. Are there any questions about this other than, yes, I've made an error here. I've done that error on purpose, and I want to use this as a segue to doing debugging. We're okay? Okay, awesome. I see 2 big thumbs up, and they're enthusiastic. So let's keep trucking on. All right. So I'm going to go back to my main.c, and I'm going to call this function now. I want to test my destroy list function. So I'm going to make a new test here, void test destroy list. I'm going to say int list is equal to create list. I got to create one to work with, and then I'm going to say list is equal to destroy list. And then I'm going to say if list is not equal to null, printf fail, else printf pass. All right. I'll call this function here test destroy list. I'm going to make this. So I'm going to open up a new terminal here, make, and it compiles. So we're good to go with that. I'm going to run it. Successfully created a list, pass. I'm actually surprised by that. Why did that work? The while loop is never run. Because there's no elements in the list. You're right, thank you. Yeah, of course, there are no elements in the list. There are no elements in the list. Yeah, okay, of course, there are no elements in the list. Okay, so let's implement our next function here. Let's implement insert front here. So what I'm returning back from insert front is going to be the size of the list that I have made the change to. So let's do that. Insert front. This takes as input an int list pointer and the item that we want to insert into the list. This is basically going to make a new node and insert it to be the new head of the list. This is the way that this is going to work. We're always going to stick it in at the front of the list. The preconditions here are must not be null, must be a valid list. There's no precondition on the value that I'm passing in here because you can't pass null to something that is like a stack allocated variable. It either has a value at compile time or you didn't write the code. Those are the only options that you have here for validating what an integer is. So for us, for now, that's what our precondition is going to be. So I'm going to say validate list one more time here. And I'm still going to do if list is not equal to null. So defensive check to make sure that I still haven't passed null in here at runtime. Then what I'm going to do is I'm going to want to start allocating one of these new node structures. So I'm going to declare a pointer up here, int node, pointer called new node is equal to null. Node is equal to malloc size of int node. And then what I'll say is if node is not equal to null, node next is equal to list head. So whatever the current head of the list is going to be the next of this node. Node, and then I'm going to have to go back up to the top because I forget what I called this, this structure, its value. The node's value is going to be item. And then I'm going to finally say here that list head is equal to node. And then I'm going to validate list. So the post condition here is that after I've made the change, it should still be a valid list. I'm actually going to take this right out and I'm going to put it way down here. I'm going to put it here in the if this is not equal to null part. If I have returned anything from this, if I've made any modification, I want to make sure that my list is valid. And then the last thing that I want to return is return list, and then I think it's called count. I'm going to go back up to the top and check that. Yes, it's called count. And that reminds me here that we need to say list count plus plus. Okay, so I'm going to make this one more time. I'm going to run it. It still works. I'm going to open up my main file here. I'm going to add a new function here that's testing insertion. I'm going to make a new list. I'm going to insert a new value into it. I'll say int size, size is equal to insert front. List, shout a number please, anyone? 8. 8 is the new value that's going to be in our list, and then I want to say if size is equal to 1. Printf pass. Else fail. And then I will finally call test insert list here in my main function. I will make it function does not return, non-void does not return. What did I say at the end of that? Did I put int there? Yes, void. All right, main. Everything seems to pass so far, so that's good. Okay, so let's go back into our test here, and I'm going to insert a value. Insert list, insert front, list. Give me another number. Oh, no, that's too predictable. Some other number. 3. Make main. Segmentation fault. Awesome. Okay, good. This is good. This is exactly what I was hoping for, I say confidently. Yeah, okay. So now what I want to do is I want to start doing a little bit of debugging with this code. My make file here has the -g flag set. So remember that if you want to do debugging with C, if you want to do any debugging with C, you have to pass this -g flag to the compiler to say, please include all variable names and source code in the compiled file so that my debugger can actually do something with it. So I'm going to say lldb main. Oh gosh. This is a fairly new laptop to me, so I haven't actually done a lot of stuff on it, and apparently I haven't used my debugger on this system yet. So I'm going to say lldb main, and once we're in the debugger, the general flow here is that with segfault, you can pretty much just say run and let it segfault, and then we can work our way backwards from that. You can do stuff like setting breakpoints. So one of the ways you can set a breakpoint is to use the b command and then the name of the function that you want to break on. Or alternatively, you can put line numbers here to say, I want to break on this specific line. Because this is a segfault, I'm just going to run it, and I'm going to let it crash to tell me where it's getting the segfault issue from. So I'm going to hit R here to run. It's going to do something, and then it's going to segfault. And then what it's going to tell me is that it is not able to keep going through current to current next in my validate function. Okay, so I'm going to hit BT here. BT is backtrace. That's going to print out all the functions that I have been called to get to this point. And what I'm seeing is that it's in the main.c at line 58, and then destroy list at line 25, and then in the destroy list function itself at line 68. So there's something going on with my destroy list function that's making a change to the list that's preventing it from exiting this loop, or exiting this loop in a state where I'm getting current set to null. So what I'm going to do is I'm going to set a breakpoint at test destroy list. So that B is, and then test destroy list is the name of the function, and I'm going to hit R. I want to rerun this process. Running will kill it and restart. Yes, please. So now I'm starting here at the test destroy list function. I don't think the problem is in my create list, so I'm going to hit N here, but I can do things like print out list. Printing out list gives me just the address, but if I do p asterisk list, so dereferencing it, it will tell me like this is the contents of the structure that you're pointing at right now. If I step into insert front, so typing S and pressing enter lets me step into a function to be able to start debugging stuff. I can then continue on, and I don't think it was here that we were getting that segfault, so list is not equal to null. I'm doing the malloc, I'm making changes to the list structure. And then if I p list here again, p list, it will give me the structure of what this looks like. So head is no longer equal to null, count is 1, there's something that's being pointed at by that. If I do p list arrow head, it's going to print out what the node looks like. Because I've got the asterisk at the front there, it's able to tell me what that node structure looks like. LLDB, there's a ton of stuff that you can do with LLDB. Did you look at LLDB in 2160? Some of you, lots of you, all of you? Who didn't look at LLDB? You did it in 2060, okay. If you want more information about that, I'm going to point you at the course webpage. But I'm just going to go straight to this textbook. If you want more information about this, there's a debugging chapter in this Intro to Tools and Techniques book that will point you at things like cheat sheets for the debugger and stuff like that. This is a good resource to get caught up with debugging stuff. I'm going to stop at this point. I'm not even going to finish debugging my own code. I'm not going to finish doing the list, because the list is not the important point of this exercise. The important point of this exercise is, let's take a look at doing debugging. Let's take a look at using make. Let's take a look at doing defensive programming and doing a little bit of design by contract. That's the main goal for this exercise. All right, I will post this code up, so if you want to complete it on your own, just as an exercise to remind yourself of all this stuff, then you're more than welcome to do that. Are there any questions about this before I move on to something else? Sure, how to start it? So I'm going to quit this. Yes, I do really want to quit. In this directory, I've got this main program here. So what I'm going to do is lldb, and I'm going to pass it the name of that program that I have compiled. And I've got that -g option in my makefile. Once I'm here, I can either set a breakpoint with the b command and then the name of the function that I want to stop executing on. Or in my case, because I'm segfaulting, I can just hit R to run, and then it will eventually segfault and then just stop for me. Yeah. So if you want to debug something that's a library that doesn't have a main function, I got to be honest with you, I'm not sure if there's a straightforward way to do that. There might be. I'm not aware of it, though. If someone's aware of it, please share that on our course forum so that other people can see it. But I'm not sure if there's a way to do debugging without writing something that actually calls and invokes those functions. Yeah. All right. OK, so I'm going to quit lldb for realsies this time. And I'm going to go back to my slides here. And what I want to do right now is to take a look at the course schedule for week 2. So I posted this yesterday. I'm going to do my very best to always post this next week's schedule on Thursdays so that we can point at it and look at it in class on Fridays. I'm going to go to the course homepage. I'm going to click on content here, and I'm going to go to course resources, and I'm going to go to, I'm actually going to go through to lectures because I try to put it here as well. So if I go to week 2 and I click on this, week 2 topics, the things that we're looking at next week are about file systems implementation. So the learning outcomes that I've got for you here, I try to make it clear where I'm expecting you to get these learning outcomes from. I don't put in class in all cases, but generally in class, we will talk at least superficially about all of these different learning outcomes. But in that I'm asking you to read chapters from the textbook, I want to make it clear what you should be getting out of that chapter. So the learning outcomes that are here, these are the things that I want you to be able to do by the time we're finished next week. And then I've got references to the chapters that I'm looking at for where those learning outcomes are coming from. But again, we're going to do a lot of this stuff in class, so you'll see some of it at least superficially in the classroom. The required readings, I'm going to remind you about the structure that I have here. This little icon on the left side is the reading notes that I kind of wrote for myself when I was going through this chapter. So at the beginning of each of these reading notes chapters, I put this little note here that basically says, like, this is me reading the textbook and then like taking notes while I'm doing it. This part, you are in no way obligated to read. This is 100,000% optional. This is just for you to have some other extra resource that's somebody else thinking about it while they're reading it. There's a lot of things in here, like I said, that are like, I'm writing down and saying, hey, that's cool. I'm trying to rephrase things that I see in the textbook to put it in a different set of words to help myself understand it. I'm asking questions about things. Sometimes I'll kind of say like, oh, they answer that later, or I may never answer it because I don't necessarily know the answer to that question. These are 100,000% optional. You are not in any way required to read these reading notes. They're just there for you to get a sense of what I was thinking about as I was going through it. The other thing that you'll see with some of the chapters here is this YouTube icon this is a summary video of that textbook chapter. The summary videos are meant to be, you can choose for chapter 40 to either read the chapter or watch the video. I don't really care which one you do, but you should consider them to be effectively equivalent to each other. Watching the video should give you exactly the same things as what you're getting by reading the textbook chapter for that one. You do not have to do both. You're not obligated to do both. They're just kind of like pick one that works best for you and choose that option. I'm also marking certain parts of these chapters as optional to read. There are some sections that are not really relevant to what I care about in this unit, and there are some things that are kind of like a little bit outside the scope of what this course is going to be. So when I see things like that in the textbook, I mark them as explicitly optional for you to do. To give you some brief introduction to each of these chapters, the first one here, files and directories, a lot of this is going to be like overview of the idea of a directory structure, and then an overview of the APIs that you use to interact with Unix systems. So how do you use open and read and write and that sort of idea. The file system implementation chapter, this one goes through the description of an implementation of a file system that's called VSFS. This is really similar in practice to a real file system that's used on Linux called ext2. We'll talk a little bit about VSFS next week in class, but the main thing that I want to spend time talking about in class next week is a different file system called exFAT. exFAT is a real actual file system that's used in real practice right now in probably everybody's device. There's a part of your machine that uses exFAT or FAT to do something on all of the devices that you have right now. So that's going to be the bulk of what we're looking at for next week. Does anybody have any questions about this? Yeah. My expectation is that you should be reading these before lectures, so before the week starts. That's my expectation. You're not going to be like unable to participate in class if you are not able to get these done. I'm going to try to like understand. Everybody's got a life. Everybody's got a life. Everyone's got a job. They're doing stuff on the weekend. I get that. You're not going to be completely unable to participate, but your participation in what we're talking about in class next week will be greatly increased by having read these chapters. Reading the chapters doesn't necessarily mean spending 6 hours like in granular detail, deeply understanding every single word that's written in there. Some of it is just getting a sense of what's in there and then going back later and reviewing what that chapter looks like for the parts that you do need some extra stuff with. But having some superficial understanding of the overall structure, having seen the keywords before will help a lot with what we're doing. Does that answer your question okay? Okay, awesome. Yeah?
In the textbook, there's like the homework chapters. Do you recommend doing that, or like because we're jumping around too much in the book, it's going to be...
That's a great question. There are homework sections. Should you do them? If you want to, it would be great practice. I have not done them, so I can't even comment on how good or bad they are. I want to assess you in my own way. I mean, I think that they're probably pretty good exercises to do, but I haven't done them, so I can't actually comment on whether or not they're going to help you. These chapters are mostly self-contained, so my guess is that you'd be able to do most of the exercises that they have there if you have the time to do it. Yeah. Any other questions? All right, okay, cool. So let's go back here, and I want to introduce us to the first sentence in chapter 39. Thus far, we've seen the development of two key operating system abstractions: the process, which is a virtualization of the CPU, and the address space, which is a virtualization of memory. This is the very first sentence in the chapter that I've just asked you to read, and I've just told you stands alone on its own. It stands very well alone on its own. What the hell does that mean? What the hell does that mean? Okay, so what I want to do is I want to spend some time running some processes on Aviary, and I want to spend a little bit of time taking a look at this idea of what an address space is. I believe that from Comp 2280, you have some superficial idea of what an address space is, in that you would have done something with addresses, you would have had to do some kind of decoding with addresses, and you would have had to do something with the stack area of the address space. But again, in terms of review and stuff, let's just get all on the same page and make sure that we know what this visualization looks like. While we're doing all of this, what I want you to do is spend some time thinking about what we were thinking about last class. What are we asking the OS to do? I'm going to bring this question up specifically when I'm doing certain things, and then also what does the OS need to keep track of to do those things? And again, I will bring up this question as we're doing certain things as part of this exercise. I have posted up on the course webpage for today's lecture I'm going to make this a little smaller so I get my side panel back here. I've posted for today's lecture this process code zip file. Your accounts on Aviary should be enabled at this point, and I would ask you to politely follow along with what I'm doing here in terms of connecting to Aviary, partly to make sure that you can still connect to Aviary. If you can't, follow along with me by watching what I'm doing, and then also follow up with the announcement that I made on the course webpage in terms of figuring out who to contact to make sure that you can change your password if you're not able to log into Aviary. So I'm going to go back to my terminal here. I'm going to zoom out. I'm going to quit my broken list. I'm going to quit my list header. I'm going to close a terminal, and I'm going to change back a directory here to process code. So I'm going to just quickly step through this code on my machine, and then I'm going to transfer it to Aviary to help remind you of SCP, and then we'll try to run it and do a couple of things with that. So this is an extremely exciting program that prints out a letter over and over and over again until the heat death of the universe. That's all it does. It doesn't do anything else, and that's it. I get as input on the command line something with a function called getOpt. You probably haven't seen this before. I don't think that we have done this in 2160 in a long time. It's straightforward to use getOpt if you want to. This is actually code that I just pretty much copied from the example section in the manual page. You can take a look at man3 getOpt if you want to see this. The examples is closer to the bottom of the manual page that describes how to use it. But the idea is that if I run /print and then give it a letter on the command line, it's just going to print forever that same thing over and over and over again. I'm going to quit this, and what I'm going to do is I'm going to copy this to Aviary. So quick reminder, SCP, your username at aviary.cs.umanitoba.ca. I'm copying this as a directory, so I'm doing -r. If you're copying the zip file to Aviary, you wouldn't need to do this, but it also won't hurt to have it. I'm going to say SCP to Aviary. I want to copy process code. And then what I'm going to put at the end of this is colon. I want to copy it to my user directory. The colon just says, like, copy it to my user directory. Press enter here. I don't have to type in a password because I've copied my public key to Aviary. If you want to learn more about that, you can use this command ssh copy ID. This will generate a public ID, public key, and then it will send the public key to Aviary so that you don't have to do passwords every time you log in. I do this because I hate typing my password in all the time, but my password then expires and I don't know about it. So take that for what it's worth. You will have had to type in your password. I'm going to SSH to Aviary now. And what I'm going to do is I'm going to change to process code. I'm going to make, and I'm going to run this code. So print -c letter A. It's extremely exciting. It's super duper exciting. What I'm going to do now is I'm going to open another terminal here, and I'm going to SSH to Aviary again. But I'm not going to SSH to Aviary. I'm going to SSH directly to hawk.cs.umanitoba.ca. Aviary sits in front. It's this. Do we know the joke of Aviary? All right, okay. Yes, I have 1 minute to tell this joke. An aviary is a big bird cage. It's a giant bird cage. All of the Linux machines, all of the hosts on the Aviary group of machines are all named as birds. This is a giant birdhouse, but there's a meta joke here. The meta joke is that Aviary is what's called a round-robin DNS entry. Robin, yes, round robin. So every time you connect to aviary, it's just going to be like you're going to go to the next host, and the next person goes to the next host, and the next person goes to the next host, and then we go back to the beginning again and just keep on cycling through. But you can connect directly to a specific machine by typing in that specific machine's host name, .cs.umanitoba.ca. So I can go directly to hawk.cs.umanitoba.ca. All right, so here's something I am entering here, print -c uppercase A. We were asking this question before about C code. Now I'm asking about something else. What am I asking the operating system to do? Don't answer the question, just think about it. What am I asking the operating system to do here? And what would the operating system need to do to keep track of to be able to do that thing for me? Don't answer the question right now, just think about it. I'm going to hit enter on my keyboard. I'm going to do something here that's called job control. So I've got a program that's running. I'm going to hit Control Z on my keyboard. Oh no, I'm going to quit this, and I'm just going to do it on my own machine because I want this to actually work. I'm going to make, and I'm going to run print, and I'm going to hit Control Z on my keyboard. And so what I've done is I've suspended this job. I've said pause. I would like to have control back. I'd like to have control back so that I can start typing things in my shell. What have I asked the operating system to do? And what does it need to keep track of to be able to do that for me? Don't answer that question, just think about it. I'm going to type in another command on this other terminal. The reason that I connected to Hawk again is because I have to be connected to the same machine to be able to do this, but now I'm running this entirely on my laptop, so I can do it entirely from here. I'm going to run a command that's called ps. PS is process, basically list the currently running processes that are on my system. This will say, I want to see which programs are currently running right now. PS by default doesn't really print much. It prints out fish, which looks kind of weird, but fish is the name of the shell that I'm using on my system. And then it prints out PS. It's also running itself right now. I'm going to say PS-A. PS-A now starts to print out a little bit more. There's other stuff that's running on my system here, GNOME session, and then bash, and then tmux. Tmux is the program that I'm using to split my terminal like this. I've also got print, which was the name of the program that I just asked to run over here. I hit Control Z on my keyboard, and it's not running anymore. It's not running anymore, but it's still there. And then PS at the bottom. Okay, so I have this program that's running right now, but it's not doing anything. I'm going to type BG on my keyboard here and press enter. And now it's going to start up again. It's going to start printing this out. Okay, so what have I asked my operating system to do? And what does it need to keep track of to be able to do that? Even though this is typing stuff out and kind of messing things up, I can keep pressing enter and get a prompt back. The prompt is where I'm allowed to start typing things in. So I'm going to say print -C, and then I'm going to print out B this time instead. What have I asked my operating system to do, and what does it need to keep track of to be able to do that for me? I'm going to pop over to my other shell here. I'm going to say PS-A. Now there's 2 entries of print there. There's all that other stuff still, but there's now 2 entries of print. I'm going to hit FG on my keyboard. I'm going to hit Control-C on my keyboard. I'm going to do PS. Control-C has terminated one of them. The other one is still running in the background. I'm going to hit FG on my keyboard over here and bring that program to the foreground again. What have I asked the operating system to do, and what does it need to keep track of to do that for me? I'm going to do one last thing here. I'm going to change directory to proc, and then I'm going to put this number here. This number is in the PID column. So 36385. Here is a directory that has a lot of stuff in it, a ton of stuff in it. The thing that I really want to take a look at right now, I'm going to hit Control A and then Z on my keyboard to zoom in here. I'm going to take a look at this file in this directory that's called maps. This file tells us about the current address space of this program that's running right now. So I'm going to come back to this in just a second. I'm going to hit Control C here. Here, I'm asking my operating system to start running a program. That's what I'm asking my operating system to do. I'm asking my operating system to start running a program, and it has to do stuff like keep track of, well, all the running programs on my computer. It's got to keep track of all the running programs on my computer. And when I type in that PS command, it's listing some subset of the running programs. We're going to take a look at lots more about what else is going on here, but the distinction that I want to make, or the idea that I want to drive home here, is that we're asking the OS to run a program. A running program is called a process. So proc/proc stands for the process pseudo file system, but it's information about processes. This is my address space layout. And if you remember from Comp 2280, and I'll draw this picture out next time, at the very top here, this is all of my, this is all the list of that program. It's the entire path of that program. The very top is my code section. Beneath that is literally labeled heap. And then at the very bottom of my address space here is labeled stack. I'll draw this as a box diagram next class, but for now it's enough for us to have seen this idea that there are ranges of memory that are being allocated to this thing. So at this point, you should be able to do 2160 again. You should be able to do all of 2160 again. And at this point, you should be able to describe at a basic level how the OS is managing processes. That's it for today. I hope you have a great weekend, and I'll see you all on Monday. Bye, everyone.